Okay, welcome back. This is the second part of the introduction, or actually Gauss's law. And in this part, I'm going to concentrate on the application of Gauss's law, specifically how to calculate the electric field using the idea of this part, finding the electric field using this idea of constructing a Gaussian and imaginary Gaussian surface from which we can calculate the electric field. Very simple, very straightforward approach. So we've done this example in the previous one. So the way to do that is, first we need to construct a Gaussian surface with a symmetry that matches the charge distribution. So what we want to do, we want to look at, and then obviously after that we want to calculate the integral and determine solve that to calculate and find the electric field. So the Gaussian surface is the most important thing. This is the imaginary Gaussian surface, and as I mentioned before, we have three types of Gaussian surfaces that will capture the symmetry, or basically to capture the number of electric field lines, which is the flux, all of them. And so for a line charge distribution, that will be a cylinder. For a spherical charge distribution, that will be a sphere. And for a surface charge distribution, that will be again a cylinder, except in a different orientation. So the idea of this imaginary Gaussian surface is very important. And the rule here is that I want a surface that counts for me all the electric field lines. So it's a surface by which I'm going to calculate the flux, the electric flux originating from or because of the electric charge. So let's start the application. And the first application, we wanted to find the electric field for a uniform infinite line with a positive charge, and it has a uniform, or a uniform charge per unit length, lambda, and we want using Gauss's law. Now remember, we've done this before. We've done this before in the previous chapter, and we've done it using calculus and using the fundamental definition of the electric field. And we found that after we've done all the calculations, all the integration, we found that the electric field is along the x direction, in this direction, and it's equal to this constant value. And of course, if you wanted to take as a vector, the electric field as a vector, it will be I hat in the positive direction. Okay, let's see how we're going to do that using Gauss's law. Now, the first thing that we need to do, we want to construct the Gaussian surface. In this case, this is my Gaussian surface, so that it captures the symmetry. Now, the electric field, due to the line, it will be radial. In this side, it will be this way, and on this side, it will be this way. And then I have this cylindrical Gaussian surface that I'm going to use. Now, I'm going to break this into three parts. Surface 1, which is this side, and surface 2 is this, the other side of the cylinder, and surface 3 is the curved surface of the cylinder. So that is captured here. So I break this closed surface integral into three surface integrals. Into three integrals. Okay, and I'm going to look at the angle between the electric field and the area for each surface. And as you can see, the electric field is constant. It's this way, or it's directed this way and directed this way from the other side. However, the area for each surface is directed different. So, for example, area 1, the angle between the electric field and area 1, where is area 1? This is area 1. So the angle between them is 90. That means cosine 90 is equal to 0. And for surface area 2, again, the angle between the electric field and area 2 is 90. So again, that will give me 0. However, for area 3, the angle between the electric field and the unit vector n hat, which is the representation of the direction of the area, perpendicular to the area at any point, is cosine 0. So cosine 0 is 1. That means I get the electric field is constant or uniform. It comes out of the integral. and then I get the electric field integrate over the area dA3. Okay, so the next step is simply because the area is constant, and the area, by the way, is the area of this curved region. This curved region, where the length of the curved region is 2 pi r, which is the circumference, and the width, or the height in this case, is L. So that the area is 2 pi r multiplied by L, and the enclosed charge, this charge here that is enclosed here, it's simply lambda times L. So this is the enclosed charge. If I do that, then I have the electric field is equal to lambda divided by 2 pi epsilon naught and 1 over r squared. Now, remember, so again, so this is radial, this direction and this direction. Now remember, we calculated this before. Let's see if we got the same thing. Yes, indeed, it's the same thing. Remember, this is 1 over 4 pi epsilon. If you multiply it by 2, you get 2 pi epsilon naught. And of course, then the 2 cancel, and you get lambda divided by r hat. In this case, x, which was x was the distance from the charge, and in here r is the distance from the charge. So it's indeed the same. If you want to look at the electric field as a function of r, so the electric field, when you get close to when r gets to 0, so that's the electric field is very at infinity, and then it just simply dies as 1 over r as you get away from the line. So this is from here, that's 0, and then it gets bigger, it's very big here and gets smaller as you get away from r, or from the line charge. Okay, so that's the first. The second application, we wanted to calculate the electric field due to an infinite plane sheet of charge that has a sigma, that has a surface charge density sigma. Where is sigma? Somewhere here. Yeah, so sigma is the surface charge density, which is constant. So again, we want to use the same Gauss's law. Now, this is my Gaussian surface. So this is my infinite sheet, a positive charge, and I know the electric field is directed this way. I just get the pen. Okay, the electric field is directed this way and directed this way, away from the, because this is positive. And I'm going to construct a Gaussian surface, as we agreed before, as a cylinder. So if we look at it just sideways differently, so we see that the electric field is away. That's my electric field on the top, and this is my electric field at the bottom, away from the sheet. And then I'm going to break my surface again into 3 surfaces. So this is S2, S1, and then I have S3. You notice that the angle between E1 and A1, or dA1, is 0. So that means the angle here is 0, cosine 0 is 1, and again the angle between these two guys is 0, so that means cosine is 1, and the angle here is 90, that means the cosine here is equal to 0. So I will have a contribution from this side, and I will have a contribution from this side, and will have 0 contribution from this side. So let's break down again the surface into 3 parts, into 3 parts, or into 3, S1, S2, S3. It's my S1, this is my S2, and S3 is the curved one. So in this time, S3 will give me 0. So this guy will go to 0 because the cosine is 0. The angle is 90 between E and the A, and these guys will give me 2 contributions. So if I put that in, I have this here will give me EA1 and EA2, and this guy will give me 0. These guys, the areas are the same. So area 1 and area 2, this area and this area are the same. So it's simply 2EA, and then Q enclosed divided by epsilon. So that's what I just said, and A1 is equal to A2. That means if I put everything together, that you get the electric field is sigma over 2 epsilon, and if I place sigma, remember the enclosed Q here is sigma A. Sigma is the surface charge density, which is constant, and A is the area of this cap, and this cap, right? Sigma, the A's will cancel, okay? And then I get E, the electric field is sigma over 2 epsilon, and sigma, remember, is defined as this guy over here, which is sigma, so Q over A. Now, this is exactly as we got before. So this is exactly as we had before when we did it using calculus, and this is the result now. If we want to plot this, if we want to plot notice that the electric field is constant. Okay, A is constant, Q is constant, and the 2 in epsilon is constant. So that means if I take the sigma, if I take this definition, then the electric field on this side is directed along the z hat. Remember, this is x, y, and this is z, we called it. So this is along, this is positive, constant. And at the bottom is pointing down, so this is negative and going this way. So this is z greater than 0, z just being the, vertical axis in this case. All right? So that's the electric field due to a sheet of charge, an infinite sheet of charge. The third example we wanted to look at is the electric field both inside and outside a sphere uniformly filled with the with charge. Okay? So remember, this is volume, so that means I'm going to use rho, and the charge Q, the total charge Q, will be simply equal to Q rho times V. Okay, I'm going to use this, and remember, I have to. This is my charge. The red the red part, or the red shaded region, is my charge, and he has asked me to find the electric field inside. Okay, so this is my Gaussian now, small r, and outside, that means now this is my r, and that's all. Now you should notice here that A, dA, and E, the angle between them is 0, so that means when I take this guy here, it will be E dA cosine 0 is 1. Okay, so in general, let's do it in general. So E dA cosine 0 is equal to Q enclosed over epsilon. So that means EA, because E is constant and A is constant, and A is equal to 4 pi r squared. So that means the electric field is equal to 1 over 4 pi epsilon Q enclosed divided by r squared. So the only challenge I have now is to find Q enclosed. Now, the second one, if I am here, if this is my Gaussian surface, by the way, this is my Gaussian surface when I am outside the sphere, and this is my Gaussian surface when I am inside the sphere. Now, if I am outside the sphere, the charge enclosed by this guy is simply Q. It's simply the total charge Q. So this is easy if you're doing, if you're outside the charge, if you're outside the sphere, the spherical charge. But if you're inside the charge here, then you're not covering all of the charge. You're covering part of it. That part is defined as, so this is inside the sphere, that the Q enclosed will be rho times the V enclosed. And the enclosed volume is simply 4/3 pi r cubed. And remember, r is less than the radius of the sphere. Okay, if I put things together, so I'm going to take this guy here, Q enclosed, I'm going to put it here and see if I can cancel or do some mathematics. So all I've done here, let me just get the pen. So all I've done here is just I've added, this is my Q enclosed, and I'm going to replace rho with its value, because rho is defined as Q divided by the volume, the big volume, the volume of the sphere. That's what rho is defined as. Remember, we defined this long time ago. Rho is equal to Q divided by V. Now you notice that this guy will go, okay, and this guy will go, all right, and then I have two of these will go with this guy, and then what I'm going to have, this survives, okay, that's here, and this survives is right here, and R survives, that R cube survives right here, and then I have 1R. So the electric field inside the sphere, the spherical shell, inside the spherical shell is defined by this formula right here. I derived it very, very smoothly, very, very easily. Okay, now let's move on to the second part, which is outside the sphere. Outside the sphere, that means I'm dealing with this guy, this is my Gaussian surface, okay? and a Q enclosed is simply rho V enclosed, and V in this case is the total volume, which is 4/3 pi r cubed. If I put that in, again, let me get the pen. If I put that in into my formula, then into this formula here. So this is my Q enclosed, and you see that, and again I put rho, which is Q over 4 pi thirds. So these guy will go, this guy will go, this guy will go, this guy will go, and the r cubed will go with the r cubed, and I get this formula right here. Okay. So this is the electric field due to the spherical charge outside the in the region outside. It's a little bit different, or actually it is different than the electric field when we calculate it inside. Let's compare the two. So this is if you're inside the charge. Let me just take this away. Okay, if you're inside the sphere. Oops. If you're inside the sphere, then the electric field is defined as a function of r. So E is proportional to r, linear with respect to r. If you are outside the sphere, E is proportional to 1 over r squared. Okay, let's make sure all of these guys are constants. All of this region here, which is all of this guy, is constant. Okay. So the electric field inside is linear, so it's just like this, and the electric field outside is 1 over r squared, which is like that. So if we put them together, that's what we get here. So if we put these guys together, inside the sphere is linear, okay, up to when r is equal to r, so up at this region here, and then after that it just goes when you get to r, then it gets 1 over becomes 1 over r squared. To test this, we should get at this point here the maximum electric field when r is equal to r, small r, the radius of the Gaussian surface is equal to big R. Then I should get this maximum value, which indeed I get it for both of these guys. If you put r is equal to big R, you get that, and that's called the maximum electric field, which occurs when you're sitting right at the surface of the sphere. Okay, so I'll stop here, and then inshallah next time we'll do the exercises which we most likely will do in class, and we'll look at the charges on conductors, which we'll see that the charge inside a conductor is equal to 0 because of the forces that the charges exert on each other, and we find out that the charge in the conductor is actually lives right at the surface, or placed right at the surface of the conductor, and so forth. So see you inshallah next class.